So we finished yesterday on page 4, and we did A, B, C, and D of example 7. Right. So now we'll move on to example 8, where we're instructed to use the properties of logarithms to simplify each expression so that the result does not contain logarithms of products, quotients, or powers. So what we are doing in this example is we are taking a logarithmic expression, okay, from condensed form to expanded form. So in A, right, we have log base 10 of 5 times x cubed plus y. This is one logarithm. Okay? This is called condensed form. We're going to rewrite it as a sum of difference of multiple logarithms. That's expanded. So in doing this, we are going to use the rules of logarithms at the bottom of the previous page. So I'll put those up on the overhead. And the first rule that we learned yesterday, was the product rule, right? The log of a product is equal to log of the first factor plus the log of the second factor. Well, you flip the, let me rephrase this. So this applies, okay, to the log of more than one product, right? You can have the log of 10 factors. That would be the log of the first factor plus the log of the second factor plus the log of the third factor, and so forth. So in this first example, we have log base 10 of 5x cubed times y. And I'm going to include parentheses. Remember, because the logarithm has special names, right? You can either include the parentheses or not include parentheses, right? This is the name, special name of the function. The name of the function is log base 10. All right. So we have the product of 3 factors here. So by the product rule, this is equal to log base 10 of the first factor, 5, plus log base 10 of the second factor, x cubed, plus log base 10 of the third factor, y. Okay? So that's by the product rule. So the product rule extends to more than 2 factors. Okay? You have 10 factors. Well, we can't do anything with this first logarithm. Log base 10 of 5, right, can't be reduced any further. Okay? But log base 10 of x cubed, this 3, by the power rule, right, can be brought down in front of the logarithm. So the second term can be written as 3 times log base 10 of x, and then we can't do anything with the third term. So by the power rule, we were able, okay, to expand this second term some more. So this on the left is known as condensed form, and this on the right is known as expanded form. Okay. condensed form to expanded form. So this on the left is equal to that on the right. All right, any questions on that? All right, in the next example, we have the natural log of x squared times the square root of x minus 3 over the cube root of x squared. We got to expand that as much as possible. Okay? So, using the rules of logarithms, you see that we're taking the natural log of a fraction. So by the quotient rule, that's equal to the natural log of the numerator minus the natural log of the denominator. So we have the natural log of the numerator minus the natural log of the denominator by the quotient rule. Now, the argument going into the natural log function here is a product, right? So we can expand this using the product rule. This is equal to the natural log of x squared plus the natural log of the square root of x minus 3. But I can write the square root of x minus 3 as x minus 3 to the 1/2 power, right? 1/2 power means square root. And then we have minus the natural log of the cube root of x squared, which can be written as x to the 2/3 power, right? Cube root of x squared is equivalent to x to the 2/3 power. So this is applying the product rule. And now, and when expanding a logarithmic expression, I found that the sequence that works best is quotient rule first, then product rule, and then last power. So you see natural log of x squared. By the power rule, we can bring the 2 down in front of the natural log. We have 2 times the natural log of x. And then by the power rule, this exponent 1/2 can be brought down from the natural log. We have 1/2 times the natural log of x minus 3. And then by the power rule, this 2/3 can be brought down from the natural log. We have minus 2/3 times the natural log of x. Now you might notice that we have like terms now, right? 2 log x and minus 2/3 log x are like terms, right? So 2 minus 2/3 is 4/3. So we can write this as 4/3 times the natural log of x plus 1/2 times the natural log of x minus 3. So this logarithm in condensed form is equal to the logarithm in expanded form. Those of you who got to take Math 120, we're going to learn about differentiation. Right? You got a little bit of an introduction to differentiation in this class. Differentiating this function is very difficult. Differentiating its equivalent isn't very easy. Okay? So being able to expand is the logarithmic expression like this is very important. Okay. Any questions on this? All right, so let's take a look at example 9. In example 9, you're instructed to find a logarithmic function, f of x equals log base b of x, such that the graph of f passes through the point 64, 3. So what we got to do is solve for the base b. Okay? We've got to find the base b. Maybe that's a better way of saying it. We've got to find the base b. Okay. So first I'm going to replace f of x with y. So y equals log base b of x. And now the graph of this logarithmic function passes through the point 64, 3. 64 is the x coordinate, 3 is the y coordinate. So I plug in for y, 3 in for y, and 64 for x. So we're using the point 64, 3. Now we can solve for b. We learned on page 1 of our notes that we can change a logarithmic statement to an equivalent exponential statement, right? At the bottom of page 1. So the equivalent exponential statement remember 3 is the exponent. B is the base. And 64 is the value of the exponential. So we have the base b raised to the exponent 3 has to equal the value of the exponential 64. So b cubed has to equal 64. So we take the cube root of both sides. And we get b is equal to 4. So we put 4 in for b. And replace y, right, with f of x. And now we have our logarithmic function. F of x is the log base 4 of x. And if you evaluate this at x equals 64, right, you get log base 4, 64 is equal to 3. When going from a logarithmic expression to an exponential expression, some people call this exponentiate. Going from a logarithmic expression to an exponential expression. All right, any questions on that? Please. All right. example 10, we're going to find the domain of that logarithmic function. We have f of x is equal to the natural log of x squared minus 1. Well, remember, from page 2, can't take the log of 0 or a negative number, right? So, one way of expressing the domain for this function, remember this is called the argument, is to set the argument greater than 0, because you can't take the log of 0 or a negative number. Well, you should now recognize this as a quadratic inequality. We learned how to solve those. Do you remember when we learned how to solve those? Section 1.1, first section of the semester, exam 1 material, way back in August. Okay? First week of class, we learned how to solve this. Math is cumulative, right? You bring everything from August with you to November. Okay? So, first step, make sure you got 0 on the right-hand side, which we do. Then set the left-hand side equal to 0, and find the zeros of the quadratic. So we have x squared is equal to 1. So we have x is equal to plus or minus the square root of 1. So we get x is equal to 1. X equals minus 1 are the zeros. Math is cumulative. You bring what you learned in August with you to November. Take those zeros, plot them on the real number line, and they break up the real number line into 3 intervals, and then you got to do the test point method. So minus 1 and 1 are not in our solution set because they may put in 1 or minus 1 for x, so left-hand side is equal to 0, not greater than 0. So in this first interval, minus 2 is less than negative 1. Minus 2 squared minus 1 is equal to 3, which is positive. So any real number less than minus 1 makes the argument in our natural log function positive. You can take the natural log of a positive number. So all these numbers work. Zeros between minus 1 and 1. And our argument going into the natural log function is equal to negative 1, and you can't take the natural log of a negative number. So these numbers in the second interval don't work. In the third interval, 2 is greater than 1. And our argument at x equals 2 is equal to 3. It's positive. So all these, any real number greater than 1 makes our argument positive. So those numbers work. So the domain of our natural log function here is all real numbers less than minus 1 and all real numbers greater than 1 in interval notation. Okay. Math is cumulative. Example 11. Remember, we missed 2 days of class. I said some things will be on video. The solution to example 11 is on video. I will send you an email with the link, and I will also post it on Hooks. But you have enough. We've done enough that you can be doing the website homework. Okay. So I'll send you the link to the solution to example 11 after class. Okay. So section 5.3 is solving various kinds of exponential and logarithmic equations. So on page 1, example 1, part A, right? You gotta solve the exponential equation 4 times e to the 2x is equal to 5. What is x? You gotta solve for x. So we have 4 times e to the 2x is equal to 5. So we got to isolate, right, x on one side of the equal sign. Well, this is a product on the left-hand side. So we can divide both sides by 4. Left 4's cancel. And we're left with e to the 2x is equal to 5/4. Left-hand side equals the right-hand side. So we can take the log of the left-hand side, the natural log of the left-hand side, and that has to equal the natural log of the right-hand side. Okay? So this argument going into the natural log function is equal to this argument going into the natural log. Well, from the previous section, okay, by property 3 of the natural log function, okay, this on the right-hand side, or on the left-hand side, is just equal to this exponent, 2x. Right? The natural log and the natural exponential function cancel each other, and we're left with 2x is equal to the natural log of 5/4. And now we divide both sides by 2. And we get x is equal to, I can write natural log of 5/4 divided by 2. I can write it as 1/2 times the natural log of 5/4. So that is the exact value of x that makes the left-hand side of this equation equal to 5. Any questions on that, ladies and gentlemen? In B, we have 2 to the x is equal to 10. Now, this is an exponential equation. 2 is the base, x is the exponent, 10 is the value of the exponential. The exponent x is equal to log base 2 of 10. Back on page 1, okay, in example 2, we learned how to change an exponential statement like that one to an equivalent logarithmic statement. So this is one way to write the solution to this exponential equation. Right? X is equal to log base 2 of 10. And in modern day, in your TI-84 calculators, right, you can, most of them you can calculate the log in any base. In my old-fashioned calculators, you can only calculate a log, the natural log, or log base 10. But in TI calculators these days, you can calculate logs in any base. And so this is equal to some decimal number. Okay, you type log base 2 of 10 into your calculator, then you'll get a decimal. All right, here's an alternative approach to solving this problem. And that's to take the natural log of both sides. So we have the natural log of 2 to the x is equal to the natural log of 10. And then by the power rule, this x can be brought down from the natural log. So I have x times the natural log of 2. Maybe it made more sense not to have parentheses and just write the natural log of 2 to the x. Bring the x down from the natural log. I have x times the natural log of 2 is equal to the natural log of 10. And now if I divide both sides by the natural log of 2, I get x is equal to the natural log of 10 over the natural log of 2. And again, using your ln key on your calculator, you type in ln of 10, hit enter, that's a decimal value. There's a decimal value. So we got two answers. We got log base 2 of 10, and we got the natural log of 10 over the natural log of 2. Those are equal, believe it or not. Okay. And this is an example of what is called the change of base formula. The change of base formula is log base A of x is equal to the natural log of x over the natural log of a. And that's showing those two solutions, right? Shows the change of base formula is. Okay. So both answers are correct. Both answers have the same decimal value. Any questions on that? All right, in C, we have 2 to the x is equal to 7 raised to the 3 plus x power. So you notice we got an exponential left and exponential right with different bases, but we cannot rewrite these with the same base. So we have to use some other approach. And again, in the sciences and mathematics, the natural log function is our workhorse. So we can take the natural log of both sides. We have the natural log of 2 to the x is equal to the natural log of 7 raised to the 3 plus x power. And now by the power rule, I can bring the x down in front of the natural log on the left side. And on the right side, I can bring down the 3 plus x in front of the natural log. And now you got to be careful with algebra. Okay? So we got to solve for x. Well, natural log of 7 is a real number, right? So type in natural log of 7 on your calculator, you get a decimal. So we're going to distribute it inside the parentheses here, just like you would if this was the number 5 out here. So we have x times the natural log of 2 is equal to 3 times the natural log of 7 plus x times the natural log of 7. So we distribute. Well, now we want all the x's on one side, so we're going to bring the x times the natural log of 7 to the left-hand side by subtraction. We have x times the natural log of 2 minus x times the natural log of 7 is equal to 3 times the natural log of 7. Okay? Now we emphasize, natural log of 2 and natural log of 7 are real numbers on a real number line. Okay? Use your calculator and you can see their decimal value. Okay? All right, so on the left here, we have a difference of 2 terms. X is a common factor, so we can factor out the x to the left. And we're left with natural log of 2 minus natural log of 7 in parentheses is equal to 3 times the natural log of 7. This is a product. So now I can divide both sides by what's inside the parentheses. And I have x is equal to 3 times the natural log of 7 divided by what's in parentheses here. Natural log of 2 minus the natural log of 7. And again, this on the right-hand side equals a decimal, right? It has a decimal value if you use your calculator. All right. Any questions on that, ladies and gentlemen? All right. In D, we have 2 times the natural log of 3x is equal to 4. So again, right, I can divide both sides by, right, this is a product. I can divide both sides by 2, okay? Twos cancel, and I'm left with the natural log of 3x is equal to 2. Now, since the left-hand side is equal to the right-hand side, I can make both sides exponents on the number e. Left side equals right side, so e raised to the left side is equal to e raised to the right side. Okay. They're equal, so I can make them exponents on the number e. Well, property 4, the natural logarithm function, says e raised to the log of e raised to the natural log of x is just x. So this on the left, e raised to the natural log of 3x is just equal to 3x. The natural exponential function and natural log function are inverse functions of each other. They cancel each other, and we're left with 3x on the left is equal to e squared on the right. And now we divide both sides by 3 to get x is equal to e squared over 3. E squared, remember e is equal to 2.718, I think it's 28, blah, blah, blah. So e squared is just this number here, on the 2.718 squared. Any questions on that, ladies and gentlemen? All right. In E, we have the natural log of x minus 1 minus the natural log of x minus 3 is equal to plus 1. What value of x makes the left-hand side equal to 1? Well, you'll notice that on the left-hand side, we have a difference of natural logs. And by the quotient rule, right, the natural log of u over v is natural log of u minus natural log of v. If we switch the two sides of this equation, we have the natural log of u minus the natural log of v is equal to the natural log of u over v. Right? So this argument, what a natural log is like u in our rule over there, and this is like v. So the left-hand side is equal to the natural log of u over v, which is x minus 1 over x minus 3 in this case. So that's the application of the quotient rule in reverse. Okay. Now, since the left-hand side equals the right-hand side, I can make the left-hand side and the right-hand side exponents on the number e. So I have e raised to the natural log of x minus 1 over x minus 3 is equal to e to the first power. Well, by property 4, property 4, right, the natural log function, that on the left is just equal to what's in parentheses here, right? Natural exponential function, natural log function cancel, and we're left with x minus 1 over x minus 3 is equal to e to the first power, which is just e. Right? And e is equal to 2.71828, right? Something like that. So solve for x. Got x in the denominator here, so we multiply both sides by x minus 3. x minus 3's cancel on the left. We're left with x minus 1 on the left. Okay. And now on the right, we got to distribute the number e. And so we have e times x minus 3 times e. Now I want to emphasize this is e times x, which is different from e raised to the x power. So don't confuse the two. Okay. Well, now we need all the x's on one side and everything, but all the terms without an x on the other side. So we can subtract e to the x from both sides. And we have x minus ex minus 1 is equal to what, minus 3 times e. And then we add 1 to both sides. And we have x minus e times x is equal to 1 minus 3e. Now on the left, I can factor out an x, and x times 1 minus e is equal to 1 minus 3 times e. Remember, e is a real number, 2.718. And now I divide both sides by 1 minus e, and I have x is equal to 1 minus 3 times e over 1 minus e. That is the exact value of x that makes the left-hand side of our original equation equal 1. Any questions on that? Yes, ma'am.
Where did the other
The other x.
No, towards the end. This one.
Here?
Yeah.
Well, this is x minus e times x. If I factored out an x, right, each term has x in it. So I factor out an x, and what I'm left with is 1 minus e. If you distribute the x inside parentheses, you have x minus ex. All right, good question. So have a good weekend, and I will see you Monday. We'll finish this up on Monday.